Hello, everyone. Welcome back. We are online. This is the session AI and Machine Learning for Software Engineering Part 2. I'm Fabio Calefato from the University of Bari, and I will be chairing this session. Just a quick look at the schedule. We have 4 papers, 2 full papers, and then 2 short ones. Just a reminder for the authors, please try to stick to the time indicated here. Otherwise, I will have to jump in and remind you to conclude. So let's start with the first speaker, Yangyang Shu, and he's presenting the paper Perf-AL, Performance Prediction for Configurable Software through Adversarial Learning. Thank you.
Okay, hello everybody. My name is Yangyang Shu. I come from University Technology of Sydney, Australia. My supervisor is Guandong Xu. Today I will present the topic. The title is Perf-AL, Performance Prediction for Configurable Software through Adversarial Learning. Okay, let's start. Today I will introduce my topic from these five aspects. The first is background, and then I will introduce my motivation and then method, and I will introduce my experiments. The last is conclusion. Okay, firstly, I will give the background. In this topic, I want to use a machine learning technique, that is adversarial learning technique, to solve the configurable software problems. We first formalize the problem of performance prediction for configurable software as a regression problem. The mapping from any configuration options of a system with n fusions to its performance value can be formalized as the left section. Yeah. The first line means x is numerical values, and the second line x equals 0 or 1 is binary form. Table 1 gives an example of a software performance function and its configurable space. This software system has 11 configuration options from this table, and in which 8 options takes binary values and 3 options takes numerical values. Manage the time performance of all possible configurations of the system is difficult and costly, demanding a lot of time and efforts. So the challenge here is to use a small yet effective sample to predict for all other configurations with high accuracy. Okay, then I will give the motivation about this paper. In this paper, we focus on predicting software performance by using a small configuration sample. Counter approaches just focus on traditional machine learning methods such as CART method or SPLC method. These approaches usually require a large amount of training samples, and the prediction accuracy relies heavily on high-quality samples. But in our method, we propose a model called Perf-AL to address these problems through adversarial learning. Yeah, in this paper, the generator network output predictive values as close to the ground truth level as possible, and the adversarial network identifies and distinguishes the predicted values of the generator network from the ground truth value distributions. This discriminator network, just like act as a teacher, can judge which value from ground truth, which value from prediction. Yeah. Maybe the question is why we use adversarial learning? Because adversarial learning, as a teacher, judge prediction of ground truth to enable the trend distribution close to the ground truth discussion by adjusting the model parameters so that the smallest configuration symbols finish the best performance. Okay, the next section I will introduce my method. In my method, I propose firstly I give the sets. In the sets include x represent the binary or numerical. Y is a software performance value, and in this picture we can find that we just want to use a general network combined with several different regulations technique, include dropout, L1 regularization, or L2 regularization, to output prediction values as close to the ground truth labels as possible. With the use of generator network, we can get the prediction about the software performance. And then in the adversarial network, we can find in this section. Yeah, in this section we give the discriminator network, and this is our object function. With the use of adversarial learning, our network identifies and distinguishes the predicted values of the generator network from the ground truth value distribution. The generator and the discriminator compete with each other by refining the prediction model iteratively until its prediction values converge towards the ground truth distribution. And then we can combine these two sections. So we can find, we can give our object function. In this object function, this weight alpha. Alpha represents, if alpha equals 0, maybe this is GAN model, generator adversarial network. But alpha is very bigger, this model just like general network without GAN. And then in our object function, we use negative log dgx instead of the log 1 minus dgx. And then we can give our algorithm. In our algorithm, in the number of the training items, we firstly training the D network in the K1 steps, and then we train the G network, the generator network, in the K2 steps until our algorithm conversions. And then we give our experiment. In our experiment, I use 7 databases, the 4 databases with binary configuration options, and 3 databases with binary or numerical config options. This information shown in the table 2. And then we give the 2 questions. The first question and the second question is that our proposed approach can improve performance on binary options and numeric options. The answer is our approach performance best in the binary and the numerical options on the datasets. And the third question is, what contribution does the adversarial component hold for our proposed model? Adversarial component improves the prediction accuracy with few samples. And the last question is, what kind of regulations should be used to achieve the best performance? In our paper, we use L1, L2, and dropout. We find L2 achieves the best performance. And we can, in order to answer question 1, question 2, we can give 2 tables. The first table is on binary configures. The second table is on binary and numerical options. We can find that our proposed method Perf-AL performs best in these 2 kinds of config options. And the third question is, what contribution about adversarial learning? We can see from these 3 pictures. In the left pictures is the earlier iterations, and in the middle pictures we find this is with ordinary deep network. Okay, the red one is ground truth and the blue line is prediction, and we can find that the right photo is that the gap between red one and the blue lines very small. So the right model, our Perf-AL have a best performance. So the first question is that what kind of regulation should is best? We can find in table 5 compared L1 and dropout, L2 techniques perform best. So we use L2 into our model, our Perf-AL. We can get the table 6 in the other database. And our method Perf-AL have a best performance. Okay, the conclusion we get is that firstly, our proposed learning approach can put a correlation between the prediction and ground truth. And the second conclusion is that our Perf-AL model is able to work with both binary and numerical configuration options. And the last one is our experimental results on 7 public real-world datasets demonstrate that Perf-AL output the state-of-the-art software performance prediction method. Okay, this is my presentation. Thank you. Any question, please?
Thank you, Yangyang.
Thank you.
For your interesting talk. Let's see, there are no questions yet, so I get started. Meanwhile, hopefully someone else will jump in. So one question is, I've seen that in the presentation you mentioned that the experiment data sets at different sites in terms of line of codes. But I'm more recently interested in the number of configuration options. I remember there was a range that I think the largest was 38 configuration options. I might be wrong. So the question is, will your algorithm Perf-AL scale to a larger system that have a larger number of configuration options? So do you have any understanding of that? What will be the performance if the Perf-AL was applied to larger systems with a larger number of configuration options?
Yes, in our experiment, I use 7 datasets, and we can, as we can see from this experiment results, we can find our Perf-AL method perform best because the metric value MRE in our model has the lowest value compared with other methods from this table. Yeah.
Okay. Thank you. I see no other questions, so I think we can move on to the next presentation. Thanks again, Yangyang, for the presentation. Thank you. Next presenter is Kamonphop Srisopha. Hopefully I pronounced it correctly, or Cam more easily. Apologies. The talk is called "Learning Features that Predict Developer Responses for iOS App Store Reviews." Thank you, Cam. Feel free to share the screen. Thank you.
Can you see my screen or no?
Yes, we can see it. Go ahead.
Okay. Greetings, everyone from Los Angeles. I am Kamonphop Srisopha. Thank you for being here. Today, I'd like to give you an overview of my recent investigation, which my co-authors and I named it Learning Feature that Predict Developer Responses for iOS App Store Reviews. So I have divided my talk into 5 sections. So due to limited time to present, I was just going to give a brief overview for each section. Let's first talk about background motivation. So for so many years since the inception of the iOS App Store in 2008, the communication on the App Store has always been one way, meaning that developer is unable to respond to review directly. Fortunately, recently that has changed. The iOS App Store introduced a new mechanism that allows developers to directly respond to reviews right on the App Store. So now developers can provide guidance, like in the example on the left. In this example, developers provide troubleshooting steps for users. Or if the user is expressing the need for a new feature, but that feature has already been implemented, developer can quickly write a response to let user know that the requested feature has already been implemented in the current version. And in the last example, developers can simply just show that they listen to their users. And recent study conducted on Google Play Store reviews suggested that responding to reviews can have a positive effect on user satisfaction. They found that users are more likely to edit their review after getting a developer response. And if users edit their reviews, users tend to increase the rating. So let's now look at the review and response process. So here on the left side depicts the user side. In this example, users composing a review. So when they finish composing, they can click the send button on the top. Now the right diagram depicts the developer side. So once the review is submitted, it will show up on developers app management portal. Here, developer can see all reviews that the app receives. They can read all these reviews and decide whether or not to respond to the review. So if they decide to respond, they can click the reply icon on the right side of each review, and this will bring up the text area where they can write the reviews to that, the response to that review, sorry. So by looking at the process from the previous slide, we can identify two major pain points. On one side, currently there are no existing guidelines for user on how they should, how they should write reviews in a way that would incite developers to respond when a response may be needed. And on the other side, for apps that receive a lot of reviews, reading every single reviews and deciding whether to respond to them become a laborious process for developers. So we want to take a look at these two sides, and we want to answer the two questions. So the first one is, can we automatically identify reviews developers are most likely to read and respond to? And if so, which characteristics of a user review developers use to decide whether or not to respond to the review? So to answer these two questions, we create a machine learning model to predict whether or not a review will receive a response. So the performance of the model can tell us the potential to automatically identify reviews developers most likely to read and to respond to. And by examining the learned relationship from the model, we can understand which characteristic of a user review influence developer response. So this is the overview of our research methods. It consists of 4 major steps: data gathering, feature extraction, model construction, and feature importance. So in the data gathering step, we use our in-house crawling tool, which acts as an iOS device to collect reviews from the app stores. In the feature extraction step, we extract feature from review both with and without developer responses, and we'll use the extracted feature as input to step 3. So in the third step, we use the random forest algorithm to learn the data and predict whether a given review will receive a developer response or will not receive a developer response. And the performance of the random forest will help us answer question 1. And we report the performance using AUC, or area under the ROC curve, which is because it's insensitive to class imbalance. And we report the performance using hyperparameter tuning and cross-validation by following prior work. So again, this will help answer question 1. And in the last step, we employ a technique called permutation feature importance to assess the importance of each individual feature and groups of features to the model in the previous step. So this will help us answer question 2. So this is the summary of the data set. We selected 8 popular applications as a case studies. So this app has a response rate ranges from 10% to 30%. We ran our crawler to get all reviews and responses of each app over a period of 1.5 years. So in total, we have collected 113,000 reviews, and of those, 24,000 reviews have developer responses. So the overall response rate is about 21%. So let's now look at the wide range of feature we extracted for each user review. These features are selected mainly based on feature that prior work or related work have identified to be associated with response decision in the area of mobile app study or in similar area of study, for example, in Q&A forum like in Stack Overflow or in corporate email communication. And we also focus on features that can be extracted using tools that have been employed successfully in related work, such as ARDoc to extract intention and SentiString to extract a sentiment. We group our selected feature into 2 top-level groups, non-text and text, and then 7 lower-level groups, rating, time, vote, sentiment, intention, style, and length. And of course, there are many interesting other features that have not been considered, for example, discussion topic, or if whether a user is discussing something that a majority of other users discuss. So let's now look at the results. Based on the result, we found that we can achieve an average AUC score of around 0.84, sorry. The ROC curve, as you can see on the left side, generally stay away from the dashed line, which depicts the random classification model by large gains. This indicates that the model, which uses the extracted feature identified in the previous slides, has high ability to capture the relationship between the selected feature and developer responses. So in general, we can observe that there's a potential or opportunity to further apply feature engineering and machine learning to help developer automatically identify reviews they are most likely to read and to respond to. So let's look at question 2 for characteristic of reviews that receive a developer response. So we found that for 2 top-level categories, non-text is more important than text features. So for 7 lower category, we found that rating is the top most important lower level group, followed by time group, which denotes the posted date time of a review, followed by sentiment group and the writing style group and length. So we found that intention and vote groups did not contribute much to the model prediction. And for the individual feature, we found that rating is still the most important feature, followed by time of the release, which denotes the time in hour that has passed between the release time of the version and the posted time of the review for that version. And the third most important individual feature that we found is the positive words body, which is the proportion of positive sentiment words in the review body. We discussed the direction of relationship further in the paper, but just to keep it brief for the presentation, I'm just gonna give a brief overview of the results. So let's now look at one of the implications. So for developer side, the benefit of the study is quite clear. It is possible to help developers automatically identify review they are most likely to read and to respond to. Now let's look at the user side. So the 2 examples that I'm showing right now show a mock-up of a developer response prediction system. So based on multiple features that can be extracted during review composition, the system should be able to determine whether the user may need a developer response and then predict the chance of getting the response and suggest the step to increase that chance. So on the left side, it detects that the user is reporting an unexpected behavior of an app, but only described the bugs in a short sentence. So it may suggest the user, let's say, to increase the length by adding more relevant information, which should increase the chance of getting a developer response. So similarly, if it detects the user is asking for help, it suggests the user to submit the review at a certain time of day to increase the chance. So the system will serve as an evidence-based guideline on how to write reviews that will have an increased chance of getting a developer response. So as you can see, this has the potential of raising the quality of user feedback. Of course, users should be able to turn this off and on for those who think that this may be counterproductive or annoying. And the system should not review all high-weight features to avoid user who wants to game the system. So I will conclude my presentation with 3 key takeaways. The first is the benefit of understanding the key feature of user review that influence developer response decision is at least 2-fold. And we saw one for user review, with user side, but developer side is also trivial to realize. The next one is we have shown earlier the efficacy of random forest in predicting developer responses using the extractive feature. Therefore, it is possible to create tools that can automatically identify reviews developer are most likely to respond to. And lastly, we have shown that review rating, posted time, the sentiment, user writing style, and review length influence developer responses, whereas intention and number of votes the review has do not influence the decision. Thank you. Thank you. That's the end of my presentation.
Thank you, Cam. Thanks for the presentation and being perfectly on time. I see there's one question already being asked, but I'll start with one. I see from your presentation, and I was skimming the paper, that you use senti strength to compute the sentiment. There is, however, a growing body of literature that uses, software engineering specific tools for sentiment analysis. So I wonder, there are in
Yes.
user review, there are going to be some jargon, some words like I can kill the app or something like that. I can crash. That is in general for sentiment strength would be negative, but actually for developers would be neutral. So I wonder if you consider that. It's something you're planning on using next. If you think it did have an effect or not, something like. If you can elaborate more.
Right, that's a very good question. We actually in a process of incorporating senti strength SE to our pipeline. Right now, we just use the tool that has been employed successfully in other mobile app study. They all have been using senti strength before, but we got also one feedback from the reviewer saying that we should try.
I said before. Okay.
Right, we should try Senti-Strength SE, and we'll try to incorporate that in our future work for sure.
Okay, so let's move on with the questions from the audience. For the developer's point of view, did you think about studying detecting the reviews that will be most likely modified by the user when they are responded to?
That's a very excellent question. Yes, we are in the process of collecting data, but the problem with studying that is that right now App Store doesn't store the original version of a review after they edit the review. So we don't know like at which point they edit and after they edit the review, do they increase the rating? So in order to get that information, we have to crawl the App Store, keep crawling the App Store to detect changes. And we're in the process of collecting that data, and it's it takes time. So we'll see the data, and then after that we will study the exactly what Afnan was saying. Yes.
Absolutely. Okay, thank you. There's time for more questions. I don't see anyone coming. I actually, not a question, but I think I have feedback. So in the slides when you plotted the rock curves, I think that one way to highlight the performance of your software would be, besides showing the the random predictors, you may want to consider some sort of trivial predictor when you use the static feature that you have ready. Like I think you said that some powerful features were the time and the user rating. So I think you can use those to build a trivial predictor. Say, okay, these are the best two, but if I add the extra feature for the model, I can do this better than the other one. So I mean, it means that your software is worth all the effort, building and training and so forth. I think it would be more compelling for you to show in that way.
Yes, definitely. Thank you for that feedback.
Okay, thank you. There are no more questions. So I will think we can thank Cam again for the excellent talk, and thanks again. Let's move on to the next paper. The presenter is Sergei Shcherban. Hi, Sergei, and he's talking about his paper, Automatic Identification of Code Smell Discussion on Stack Overflow. Please, Sergei, thank you.
Hi, everyone. My name is Sergei. I'm a master student from Wuhan University. Today, I'm going to talk about automatic identification of code smell discussion on Stack Overflow. So here's the outline of my presentation. Firstly, we're going to talk about background and motivations and methodologies, study results, summary, and finally, future work. So firstly, we need to talk about code smell. A code smell is a sign that normally corresponds to more rooted problem in the program. A smell might not directly correspond to false, but it may serve as an indicator, a part of the code smell that's error prone. So there is a problem with finding kind of this discussion on Stack Overflow, I mean code smell discussion on Stack Overflow, because of the large number of questions on Stack Overflow and because of nature of tagging systems that use the search system on Stack Overflow. So there is several problems with using tags as exclusive approach to decide whether a post related to specific topics. A recent works on code smell discussion on Stack Overflow shows that many of code smell related questions did not contain any of code smell identifiers in the tags or titles. This may result in the posts that contain relevant code smell knowledge, but cannot be located if they use tags that are not within the scope of the search. Moreover, recently, Stack Overflow removed code smell as a tag because of its subjectivity. So it's become harder to find something related to code smell. So we have two research questions. First one, which machine learning algorithm work best for identifying code smell discussion from Stack Overflow? And second one, which combination of feature extraction techniques and machine learning algorithm work best for identifying code smell discussion from Stack Overflow? To solve this research question, we manage our experiment in 5 phases. First phase is input data, then preprocess text, like removing useless symbols, then extract features, then train classificator algorithm, and then evaluate trained algorithm. So key point of any machine learning or deep learning project is data. For constructing our dataset, we selected posts that contained code smell discussion provided by Tahir and his colleagues. We also scrapped a few thousand posts from Stack Overflow and manually labeled it like non-code smell post. And after cross-validate this content randomly selected post with using 95% of confidence interval. So for classification algorithms, we choose 5 classic ML algorithms like random forest, key nearest neighbors, Gaussian process, support vector machine, and logistic regression. And for feature extraction techniques, we use some simple techniques like back of words and term frequency, inverse document frequency, and some complex techniques like word2vec, doc2vec, fast text, and glow. So for evaluation our results, we use precision, recall, F1, and accuracy. We have balanced data set, but we also would to check recall and precision to make sure that everything is okay. So here's the results of first research question. As you can see on the plot, that logistic regression works pretty good. The best performant algorithm was logistic regressions, while the least performant algorithm was Gaussian process. And on the second table, you can see different combination between feature extraction techniques and logistic regression. And this table shows that 2 combinations performs better than others. First of all, back of words and linear regression, and second one is team frequency, inverse document frequency with logistic regression. We also use hyperparameter optimizations, but mostly it works pretty good with default parameters. So in conclusion, we achieved few things. First thing is that we use supervised machine learning algorithms and several feature extraction techniques to automatically identify posts that contain code smell related discussions. It can help to researcher or someone else to find it on resources such as Stack Overflow. We also create a dataset with code smell and not code smell post from Stack Overflow. We publish it online. Everyone can use it. So because of the lack of good datasets in software engineering related to software engineering, so we publish our dataset online. And the results show that logistic regression performs better than other algorithms. In future work, we plan to evaluate our best configurations on a larger dataset of discussion from Stack Overflow. We also plan to use automatic techniques to identify subtopics from the code smell discussion and capture the context of this discussion. And we also want to evaluate the utility of the classifier by classifying the unseen Stack Overflow post into code smell discussion and manually check the output. So that's all for my presentation. If you have some question, feel free to ask.
Okay, thank you, Sergei. There is one One questions, but probably two. Just let's start with this while I check the others. This question is basically asking, I think, how this approach will work with the specific test smells rather than code smells in general.
Yeah, good question. Now it works only in general, so it's just identify all code smell related questions, not by subtopic of code smells like dead code or test smells. So we plan to work. Our investigation is still ongoing, so we plan to work to identify subtopics of code smell.
Okay. Thank you. There's a question popping, so we have time. So Sergei, you have a few more questions to answer. This one from Anthony. Actually, I was going to ask this myself, something related. If you can elaborate more on the text preprocessing techniques. Myself also was also curious about, from between when you were talking about RQ1, what were the features that you used in the to compare the algorithm? I think you didn't mention it, probably. Maybe it's in the paper, of course. So again, I think I was going to ask, which feature, which was excluded and so forth.
For preprocessing techniques, we just removed useless symbols like tabulation symbols or something not related to English language, and we do not remove code snippets, and it works well, as you can see. So we did not remove code snippets.
Okay, one more question. That is more specific for the second research question about insights about talk-to-back and word-to-back. Okay, can you say more about the combination of those?
Yeah. I think it performs worse because we don't have a lot of data in our data sets. There is a lot of words, specific words related to code smells that repeated again and again, like code smell, anti-pattern. So we don't have a lot of data. So I think that's why some simple algorithm feature extraction techniques like back of words and term frequency works better than others. Also, there is a problem with using word-to-vec and doc-to-vec and fast text, like more complex algorithm, because they have some pre-trained embedding for like Google News pre-trained embeddings, but they don't have pre-trained embedding for software engineering problems. So maybe if we collect more this kind of data sets, we can pre-train these models, and it will increase accuracy of future models.
Makes sense. I put this one on screen because I think you kind of answered already. I think you already speculated why they performed worse. So you may want to follow up on YouTube or Facebook. You can keep discussing.
Yeah.
Okay, thanks again for the talk. Let's move on to the last paper of the session. The presenter is Carmen Coviello, and the paper is titled "Cluster Genetic Algorithm for Test Suite Reduction." Please go ahead.
Thank you. Good evening. I'm Carmen Coviello, a PhD student from University of Basilicata in the south of Italy. And today I'll talk to you about Cluster, a new approach based that by the use of genetic algorithm allow to reduce the size of the test suite. Regression testing is a very important activity that aims to ensure that changes made to a system under test don't alter its expected behavior. But test suites tend to grow in size as systems evolve, because more the functionality to be tested, more the test. This is a very important problem because the regression testing is usually the last operation to do before a system release or a system integration. Different strategies have been proposed to deal with this problem, and test suite reduction techniques allow to reduce the size of the test suite by removing redundant or obsolete test cases. Traditional test suite reduction approaches works on a single dimension, but recent works showed that multiple dimension techniques are appealing for test suite reduction. Thus, we define Gasser, a new test suite reduction approach based on a multi-objective evolutionary algorithm, namely NSGA2. Gasser tried to reach 3 objectives at the same time: maximize the test suite statement coverage, maximize the test cases diversity, and minimize the test suite size. Genetic algorithms are complex and adaptive procedures that start by, from an initial population and recombine them in order to obtain better solution with an iterative process. During the first step, an initial population is randomly created, and each individual of the population is composed of genes. They are joined into a vector to form a chromosome. In our problem, each individual is a reduced test suite randomly selected among all of those possible. The fitness function evaluates how each solution of the population is near to the optimal solution of the problem. In our problem, the fitness function is composed of 3 functions, one for each objective: statement coverage, test case diversity, and test suite size. The selection phase selects the fittest individual of the population and in order to pass their genes to the next generation. Then 2 fittest individuals are mixed up in the crossover phase in order to create children. We use the 1-point crossover, in which the crossover point is randomly selected for each pair of parents. The mutation step works on a single individual, and it consists in a genetic mutation. This phase guarantees variability in the population and prevents premature convergence. And this operation iterates over time, and the algorithm stops when the population converges or when the maximum value for iteration is reached. In output, we have a set of optimal solutions, and when plotted, we should have a Pareto front. This is a Gasser output example, and to select the better trade-off among the 3 objectives, we used a criterion based on the compromise programming method. In particular, we define an ideal point, such as the point with the maximum test cases diversity and test suite statement coverage and the minimum test suite size. And then we compute the Euclidean distance among this point, the green point in the figure, and all the points in the Pareto front, where each point is a solution of the population. Then the solution closest to the ideal point is selected as the best trade-off among the 3 objectives. We define 7 instances of the Gasser approach, and they differ each other for the dissimilarity measure used to compute the test cases diversity. To verify our idea in the proposed approach, we perform a preliminary experiment. And in particular, our question wants to verify if, as compared to the baseline test suite reduction approaches, Gasser can obtain a better trade-off in terms of reduction in test suite size and reduction in fault detection capability. These 2 metrics are very important because they allow to quantify to verify the quality of the reduced test suite. In particular, we ran Gasser on 19 versions of 4 Java systems, and we compare the best trade-off obtained by Gasser with the results of 9 test suite reduction baseline approaches. Results show that some instances of the Gasser approach, and in particular Gasser Hemming, allow obtaining a better result in terms of reduction in test suite size and reduction in fault detection capability as compared of the baseline test suite reduction approaches. And these results justify our research on the use of genetic algorithm to reduce the size of the test suite. In the future, we plan to extend experimentation to bigger systems with larger test suite and extend empirical assessment with a new statistic analysis and perform a study on the scalability. Thank you.
Thank you, Carmen. Thanks for being on time. Actually, we have quite a few minutes for questions. So there are no questions in YouTube, so I'll get started. So first thing first, I didn't see any link. There is any experimental package that is available for people who want to keep working from this point on?
No, up to now we are working on our future work, and we plan to publish some replication package.
Okay. Next, and let's see, no more questions. So I think you have, since your presentation, was perfectly on time, but we have quite a few minutes for question. I think you can probably spend a little time elaborating more on the experimentation, giving us a few more details, like I don't know, anything more about that, the data set, how it was built, and so forth. I know it must be in the paper, but since we have time, I think we can you can elaborate more on that, on the experimentation.
Yes, we used we run Gasser on 19 version of 4 Java system. The experimental objects are selected from SIR, and repository online, which is widely used in regression testing approach. And we select SIR because allow us to obtain detail on fault, because to compute reduction in fault detection capability, we must have information on fault in the systems, so we can compare the original test suite and its fault detection capability with the reduced test suite and the fault detection capability to compute these metrics. They are Java system.
Mm-hmm. Okay, thanks. But there's no question, but actually something that is also nice to see from some compliments from the audience. So Afnan is congratulating for the use of graphics. So no question, but I think it's good feedback for the authors and the presenters.
Thank you.
Okay, I think there are no more questions. We actually are a couple of minutes early, but there is a break now. So ESEM will be back online in 12 minutes. So thanks for being with me today, and stay tuned for the next session on social factor, will be chaired by Alexander Serebrennik. See you later.